Hi everyone, this video is an introduction to section 16.2 on the topic of line integrals. So our goal in this section is to think of integrating a function not over an interval a to b, but instead over a curve c. And such an integral is called a line integral, but should perhaps really be called a curve integral since we're integrating over a curve. And line integrals were invented in the early 19th century to solve problems involving fluid flow, forces, electricity, and magnetism. So here we go. So what happens is we start with a plane curve C, so a curve in the xy plane that is given by parametric equations. So we have a function x of t telling us what our x coordinate is doing, a function y of t telling us what our y coordinate is doing as the parameter t varies between two values a and b. Or equivalently, we could also describe our curve with a vector equation r of t. And we assume that this curve C is a smooth curve, which just means that r prime is continuous and not the zero vector. So for example, here is an example of a parametric curve, x equals cosine of t, y equals sine of t, for t between negative pi over 2 and positive pi over 2, and this would represent the right half of our unit circle. Now note that this curve can also be parametrized by letting x be given by the square root of 1 minus t squared, y equals t for t between negative 1 and positive 1. And I mention that only as a reminder that the parametrization of a curve is not unique. So there can be lots of different ways to describe the same curve. Okay, so let's get back to our integral. So again, we're starting with a curve C. We see it here in pink. So we have a curve C, which is in the xy plane, and is described by parametric equations x of t and y of t for t between a and b. And what we're going to do first is we're going to divide that parameter interval a to b into n subintervals of equal width, and let x sub I be x of t sub I and y sub I be y of t sub I. And so then the corresponding points, x sub I, y sub I, are going to divide that curve C into n little bitty curves, little bitty sub-arcs, and the lengths of those little bitty sub-arcs we're going to call delta S1, delta S2, so on and so forth. And what we're going to do is inside each one of these little sub-arcs, we're going to pick a sample point, p sub I star. And if f is any function of two variables whose domain includes this curve C, we're going to simply evaluate f at that sample point and then multiply by the length delta S sub I of the corresponding sub-arc. So we take the function f, we evaluate at the sample point, we multiply by the length of that little sub-arc, we add all of these together for each one of these little sub-arcs, and we get something that looks a lot like a Riemann sum. So here's our formal definition. If f is defined on a smooth curve C, then the line integral of f along C, so we see here the integral over C of f of x y ds, is the limit of the sum of this function f evaluated at our sample point times the length of that sub-arc. And now since this ds or this delta s refers to a length of a curve, then ds will be the square root of dx dt squared plus dy dt squared dt. And therefore, if we combine the two together, we see that the integral over c of f of x y ds will be the integral over the parameter range a to b of f evaluated at our parametrization x of t, y of t. And for the ds, we have the length of the curve square root of dx dt squared plus dy dt squared dt. So here it is cleaned up a little bit. Now, recall a moment ago I pointed out that the parametrization of a curve is not unique. There's more than one way for us to describe a curve C. So I remark here that the value of the line integral does not depend on the parametrization of the curve, provided that the curve is traversed exactly once as t increases from a to b. So this is good news. This means if I choose one parametrization for c and you choose a different one, we're going to get the same value for our line integral in the end. Great, so let's do a couple of examples to see this formula in action. Here's example 1. Let's evaluate the line integral of x y to the fourth, where c is the right half of the circle x squared plus y squared equals 16. So first we need to find parametric equations to describe the curve c. So here it is, the right half of our circle. Now, a circle centered at the origin of radius 4 can be parametrized by letting x be 4 cosine t, y be 4 sine t. And since we only want the right half of the circle, we're going to restrict t to negative pi over 2 to positive pi over 2. Recall that ds is the square root of dx dt squared plus dy dt squared dt. So in this example, dx dt will be negative 4 sine t, and dy dt will be 4 cosine t. So we get the square root of 16 sine squared plus 16 cosine squared. And now using the fact that sine squared plus cosine squared is 1, this simplifies to the square root of 16 or 4 dt. So there we go. So ds is 4 dt. And so our integral over the curve of x y to the fourth will be the integral from negative pi over 2 to positive pi over 2. We replace x with 4 cosine t. We replace y to the fourth with 4 to the fourth sine to the fourth. And then ds we found to be 4 dt. Great. I'm going to go to a new slide so we have some room to compute the integral. So here we go. I'm going to pull out the 4s. We have 6 of them. So we have 4 to the 6th times our integral of cosine of t sine to the fourth. A simple u substitution tells us this integrates to 4 to the 6th times 1/5 sine to the fifth. We evaluate from negative pi over 2 to positive pi over 2, and our final answer is 2 times 4 to the 6th divided by 5. Great. Before we do another example, let's talk about the interpretation of the line integral. What is this number giving us? Well, just as for an ordinary single integral, we can interpret the line integral of a positive function as an area. So in fact, if our function f is positive, then the integral over c represents the area of one side of the fence or the curtain that you see in the figure here, whose base is the curve c and whose height above the point xy is f of xy. So when we're doing a line integral of a positive function, the number we're getting is the area of the fence whose base is the curve and whose height is the function. Great, let's do one last example. Let's evaluate the line integral of x squared times the square root of y, where our curve is the line segment from 2, 4 to 4, 8. So first, we always need to find parametric equations to describe our curve, and in this case, our curve is a line segment. And there's a trick for line segments. So if we want a parametric representation of a line segment from the point AB to the point CD, what we can do is we'll let x of t be a times 1 minus t plus ct, and y of t be b times 1 minus t plus dt. And so you can plug in t equals 0, and that'll show you that we start at the point AB. And if you plug in t equals 1, you'll see that you end at the point CD. Okay, so in this case, since we're going from 2, 4 to 4, 8, x of t will be 2 times 1 minus t plus 4t, which cleans up to 2 plus 2t. And y will be 4 times 1 minus t plus 8t, which cleans up to 4 plus 4t. Great. All right, let's find ds. So ds again is the square root of dx dt squared plus dy dt squared dt. And in this example, dx dt is 2, dy dt is 4, and so we end up with the square root of 20 dt. And so our line integral will be the integral from 0 to 1. X squared will be 2 plus 2t squared. The square root of y will be the square root of 4 plus 4t. ds, remember, we found to be the square root of 20 dt. All right, I'm going to go to a fresh slide so I have room to work. So there we are. All right, I'm going to clean this up a little bit. So we're going to pull out the square root of 20 all the way to the front. I'm going to factor out a 2 squared to give me a 4 and a square root of 4 to give me a 2. And so I'll have 8 times the square root of 20 times the integral from 0 to 1. And when we combine the 1 plus t's, we'll have a 1 plus t to the 5 halves. So we add 1 to the exponent, divide by the new exponent, and then evaluate from 0 to 1. And our final answer is 16 times the square root of 20 divided by 7 times 2 to the 7 halves minus 1. Great, and recall, since our function is positive, we can interpret this number as an area, the area above that line segment and below the function. Okay, one final thing. Here's a quick cheat sheet if you're curious on how we find these parameterizations. So there's often just an easy way to do it for a parameterization of a circle. We talked about a line segment. Also in the case where our curve is described as a function y equals f of x or a function x equals g of y. And we'll talk more about all of these in class and dive more into line integrals then. I'll see you then. Alrighty.